Good morning, or good evening, or good day to all of you. So today we'll be talking about charging ahead and the transition to eBuses. We'll be sharing with you some practical case studies of actual data that has been generated on the buses that are running. This presentation will be recorded and a slide pack will be available for those who registered, to all those participants. We'll run for about 20 minutes and then we'll have about 10 minutes for Q&A. So if you could put your questions in the chat and we will endeavor to get back to you. On some of the previous seminars, we've had more questions than we can handle in the allotted time, and I will respond to you via email. Okay, let's crack into this. So what we're going to look at here is a specific case study, and just to give you a bit of background on how the data was obtained, we're going to roll through and I'll give you more explanation of a WSP tool called BOLT, Battery Optimization and Lifecycle Tool. And as things go, I've already spotted my first spelling mistake. Right, so this particular one was based around a client who had 3 depots, different areas, mixture of routes. Those routes had substantial change in altitude. Some routes were very city-bound and never got more than 30 kilometers an hour, whilst others were averaging over 75 kilometers an hour because they had freeway or motorway routes. For most of those, we were able to access GTFS data. It's the first acronym you can Google. And this was available, but for some of those routes, we had very limited passenger data in terms of who was alighting, who was leaving, because of the mix between RFID cards, aged population who get free transport after certain times, and also historically cash. We looked at ambient temperatures as well as the road data, and all of this fed in, as you can see on the right-hand side, the information. What were the revenue trips? What were the non-revenue trips? We'll go into a bit more detail there, the ridership as we've discussed. And then we roll that through BOLT. And BOLT looks at all the stop points, the elevation lines, the patterns, the number of routes that are added together to make the schedule, to make the blocks, which depot the buses start from, and how this rolls through. Right, so we looked at a number of buses, and so for this, we looked at the route, we looked historically, we looked at the future growth of the route, and from that we were able to extract a number of commercially available eBuses which were available at the time, and we looked specifically at drivetrains, tires, gearing, what the road network was. For some of these routes we did specific surveys. For other routes we already had road surveys, including road furniture, specific points of stops, etc. Then we looked at the depot location, all of the distances involved, and of course the traffic environment. You can see on the right-hand side over here that all of this information gets pulled in against the route. We have a look at that. We look at everything about this electric vehicle, its efficiencies, battery sizes, the electric motor specification. We look at all the parasitic loads, air conditioning, lighting, all the drivers, CCTV, etc. We look at the effectiveness of the regenerative braking. And then we look at what's the speed, what's the demand, what's the road conditions, as well as what did the manufacturer say the bus was going to do, and then we test that. So we look at the chargers, we look at how much power we can get out of them, what their efficiencies are, roll through that. Then we look at the different stop points, pull in, pull out, bus onboarding, as we said. And then we look at the different types of transition of the buses. So for Auckland Transport, we looked at an accelerated replacement, a moderate replacement, which if you look at their literature, they called option E, or purely replacement on a retirement age based on 12 to 20 years on the bus, depending on the mileage and the type of bus. Right, so as we've said, 3 depots, typically 80 to 150 buses per depot, plus the engineering spares. Buses, 6 days per week, 52 weeks per year. And you can see there the mileage, the average age, and what the residual value of the vehicle was when it was disposed. So I've tried, because this has also sucked in data from a number of other sites, I've tried to put this into common US dollar denominations, because we've got people from all around the world looking at it, and a New Zealand dollar may not mean much. So the cost of a large diesel bus is about US 480,000, and it consumes about 53 liters per 100 kilometers. Somebody's got their mic switched on, if they could just mute, please. And then typically we've looked at diesel escalating at 0.7% per annum. Now, in this day and age, as we're sitting right here now, that may need to be reviewed because of what's happening with situations in Ukraine. We looked at the diesel maintenance costs. Now, the cost of an electric bus, the capex is higher. 880,000 was at the time that this was done. There are buses that are available lower than that now, and the trend is continuing. But you've also got against that what's happening on the London's Metal Exchange with the increase of base materials cost. We looked at US dollars 13 cents per kilowatt hour for electricity and a peak charge of 345 per kilowatt. Battery life typically is 12 years, but we just took the guaranteed 10-year and we included the degradation in that. So in other words, the manufacturer overspecs the battery to ensure at end of life, the bus is guaranteed to complete what it says it would in terms of range. The minimum test blocks that we use, group of 4 buses, and then the rest of it's just information. Now, one of the things that you will see as we go through this is some of the maintenance charges are just beginning to come through, and that's because the buses are only coming out of their warranty periods now, and many of them, the maintenance was covered during warranty. But we're still seeing it tracking to the figures that we expected. Most installations, every bus started with a charger. As we've gone to larger chargers, that is no longer necessarily the case. And in many depots, we've now overlaid those chargers with queuing systems and software control to manage the maximum demand. Now, let's get into the efficiency and the operation. Typically, a charger running at about 92% after you've allowed for power in, cabling, heat, etc. And typically, we start round about the 80 kilowatt capacity. If you're going to go to fast charging, and I see we've got some questions on that, you're looking at outputs in excess of 300 kilowatts. That makes quite a difference. So now Bolt pulls all of this in. We look at the non-revenue runs, we look at diversion from the routes, and sometimes those diversions may be necessary because of roadworks. Sometimes the diversions are unauthorized, and you'd be surprised, but yeah, bus sometimes departs from its route because it went to pick up a friend or it went to go and pick up the lunchbox. So those routes are overlaid. We look at the route segment, we look at the route pattern, they're consolidated together to produce a bus block, and then we pull the groups of blocks together. And I see we've got a question on scheduling, which is a good point, because often scheduling for energy is different to scheduling for a diesel bus. And you'll begin to see that as we start to look through this. So now for the Bolt process, battery optimization and life cycle tools, we looked at the worst situation, worst traffic, coldest day of the year, so the heaters were running at maximum with the heaviest loads because the weather was bad, so nobody wanted to walk, so everybody was using the bus who could. And what that does is that gives you an energy demand on the bus, which you have to be able to meet from the battery en route, plus you have to be able to charge that bus and have it ready for its next route. So what starts to come out of Bolt is, can you do the route? Was it a success or not? When you group these routes together, was the block a success or not? Or did the bus run out of energy along the way, which you really don't want? Then as you group all of these blocks together against the buses that you have, do you have success at the depot? And now that consists of two things. So you have an architectural analysis which looks at, can we park these buses? Because an electric bus with its charger, the way it parks and the access that's needed is different to that of a diesel bus. And secondly, can we electrify the buses and complete the routes? And if you get an electrification index of well over 80%, then you know that the vast majority of those routes can be completed by the bus that you've selected. If you select a bus with an insufficiently sized battery, you might find that that electrification index drops. And I'll show you a slide later on where some decisions had to be made. This also generates, excuse me, what was the power demand and of course the maximum demand. So the first thing to look at is this graph on the right-hand side. So the dark blue line shows the topology, and you can see a bus here going up some hills early in the morning. The pale beige around it was the ridership, which was pretty low. But as it got to the top and started to run down, the ridership increased quite dramatically. And then people started dropping off. And by the time the bus got to the end of its route, it was empty. It went back into turnaround and then off to start its next route. Now, what happens here is at the end of the day, you get the opposite effect. So you get a very heavy ridership of people going up the hill, and then the bus empties very rapidly going down the hill. Bolt takes into account all of this. And on this particular one, we only used 2.8% of the battery, but because of the topology, we were running at 1.355 kilowatt hours per kilometer. Now this averages out depending on what routes your bus is running on. Overall, you now stack a number of these routes together and you begin to get a graph like this for your battery, which shows your battery charge is steadily dropping. And this particular one has a 20% safety factor in it. And so you can run a number of routes back to back, and then you need to charge. And again, the question now becomes, what is your charging regime? Are you charging everything in the depot, or are you charging en route, or are you charging at the end of your route? So from this, you're then able to pull all of the buses for all of the depots. And you can see a number of blocks here are completed, over 91%. Then 100% of the routes are covered. But as you get into some of the other more difficult routes where perhaps you've got a double-decker bus running up some very steep roads or at high kilometer per hour speeds, you might find that you've got some issues. So now looking at the depot itself. So first of all, we know that the buses can do the route, they can be electrified, and we've selected a battery size. Now we then take that battery size plus the routes and the scheduling, and we say, how much power do we actually need to charge these buses so that they're ready, for instance, at 5 a.m. to go out? We look at the maximum demand per individual charger, and then you look at your consolidated demand by depot. And bear in mind, those chargers will have different schedules as well, especially if you're queuing buses and you've got multiple buses per charger. And then we would rerun that for various battery and drive configurations, looking to optimize it. Should we go for a bigger battery, fewer charge cycles, or should we go for a smaller battery, which is a lighter bus, which is more efficient, but we need to charge it more often? And so from this, you end up with some fairly complex graphs which show you a lot of data on it. So they show you on the one axis what is the total demand out of the depot, and you can see two peaks here. The black curve here is actually showing the buses out in service and the routes that they're running. So a lot of routes in the morning, slows down middle of the day, a lot of routes in the evening. And then we look at the maximum demand and what's happening, and you'll see typically that a lot of the demand in terms of high power consumption starts after 8 p.m. at night as the buses start coming into the depot. So now here's a bus depot which has a number of routes that are run, and we picked on a number of scenarios. So for some of those scenarios, you can see here route 14, even with a 300 kilowatt hour battery, 85% of the routes were completed without a problem. But to complete that last 15%, using this charger configuration and this bus configuration, you'd need to go to nearly 600 kilowatt hour battery. Right? For some of them, you can see here route 11, even with an 800 kilowatt hour battery, you could still only complete 90% of the routes. So now you have some questions there. On that route, do we need to look at different type of storage facility? Do we need to look at a hydrogen bus? Is this suited for electrification? Do we need to change the route? So some routes very easy to do and very complete, especially where you're doing less than 350 kilometers in a day. The electric bus can handle those. Other routes, more difficult. So now this is really where the rubber meets the road, and we're coming to the end of the presentation, and this is where the data begins to get very real. So this was for 3 buses, a BYD, a Yutong, and a BYD custom route. You can see some of these routes were fairly lightly loaded. You can see the kilowatt hours per kilometer that was predicted versus what was actually obtained with that bus on trial in those city configurations, which is actually very close there. You can see the average speed that we predicted and what we actually got in the traffic. And so overall, our worst scenario was that we had a 4% error. So 96% accurate against what happened in the situation, even down to the point where we were in the worst traffic with the maximum number of stop and goes. We were able to indicate, this is the same driver that you had yesterday, or no, that was a different driver. This driver was much smoother, or this driver switched off the regenerative braking. So these are the sort of factors that were coming out. Now, this particular one is Auckland City fleet-wide, and the data has been published and is publicly available if you want to dig into it in more information, in more detail. So for the electric buses, you've got a couple of different sizes ranging from 0.7 right up to 1.41 kilowatt hours per kilometer. Obviously double decker, greater weight, greater wind resistance, etc. And you can see accordingly the liters per kilometer, that shouldn't have a dollar sign in front of it. Those are just liters per kilometer that are consumed. And then we looked at what's the cost premium. Road user charges here in New Zealand are quite substantial depending on axle weight and bus arrangements. So those had to be incorporated. And of course, we looked at what was the contractual rate of the diesel here. And at the end of it, the business case for the buses still was positive. Right, so here's some interesting facts and figures. And this information is in your slide pack, so don't worry about it. But what you will see, for instance, is we have a Yutong e-bus on the airport routes, and these are routes 380 and 309. It travels in some places at over 80 kilometers an hour. It runs at a range of 340 kilometers, and yet it consistently returns to the depot with at least 10% state of charge. Now, bear in mind that's above the 20% safety factor we would have put in for bus degradation, etc. On a large bus depot upgrade, we found typically the high voltage strengthening accounts for about 3% of the total capital cost. So it's not massive, but it is one of the factors that often has the longest lead time. Right, So a couple of other factors. If you're doing some comparisons, just look at Euro 6. If you're looking at biofuel, there are often issues around its source and scalability. And obviously the battery costs are coming down. We're seeing far better warranties. We're seeing better ranges. We're also seeing more electric ferries, which also is increasing the strength of the network. Now, I haven't focused in this presentation on hydrogen, but we are running a hydrogen trial bus here. And what we are finding that it may have a higher total cost of ownership, but we expect that to improve as the technology matures. We do have a longer range, but we're still finding that some of the refueling issues need to be resolved, not just the cost of hydrogen. Right, so hydrogen, you're looking at 2035, batteries available now. And bear in mind, it doesn't matter what storage you offer, it's going to reduce your efficiency and increase your costs. We're also trialing hydrogen heavy vehicles. So what we're seeing here is electric bus adoption rapidly increasing. Ranges beyond 350 kilometers are not unusual. We are seeing from some of the leading brands that they're expecting ranges of over 400. Battery sizes typically in that 250 to 500, but 600 kilowatt hours not unusual. Battery warranties of 10 years are now available, and just as Tesla found, savings have been achieved via software improvements and of course charger upgrades. Right, I'll switch my camera on and I'm happy to take any questions.
Thank you, Kristian. Can you hear me, I hope?
Yes, I can hear you now. Thank you.
Oh, perfect. So apologies for the audio issues before on my end. So thank you for your presentation. Thank you for the attendees today. Just you can log your questions in the question box on the GoToWebinar platform, and also the presentation is available to download in the handout box. Now, we received several questions from people who registered, so I will start with those. Can battery compete with hydrogen consistently?
It's actually a good question, because what we're seeing is that in the up to 350 kilometers, the battery is very effective, very efficient, and it will deal with that daily range with depot charging without a problem. You can go out and buy a bus now, sign for it. If you're going to go beyond that, and there are some cities where we've run into some very high, long routes where we're 550, 600 kilometers, and the bus is out of the depot 22 hours, that becomes a lot more challenging. And you've got two options here. Either you go for en route charging, where you've got top-up charging along the way, or fast charging at certain depot, at certain stop locations where the bus may need to stop for 15 minutes or so. Bear in mind, we can drop 430 kilowatts into a battery if it's correctly rated in 17 minutes. So it's less of a problem than it was. But there are still some routes where hydrogen may be the option there. But as I've said, any storage addition reduces your efficiency, adds your cost. If someone's interested in hydrogen figures, my email address is there. Flick me a note and I can give you some more data.
Fantastic, thank you. The next question is, I start with a statement and then a question. Out of depot charging is best using high voltage supply. Is current infrastructure suited to deliver this in the suburbs, either along the route or at the turnaround point?
Yeah, now again, that is very true. Because of the size of the chargers that you're using out of the depot, typically we would go to fast chargers. So in Wellington, the fast charger there is 430 kVA, and it can dump a huge amount of power into a bus in a very short period of time. So your maximum demand is high. So as this question illuminates, you do need a good high voltage infrastructure for it. In your industrial areas, it's usually not a problem because the high voltage infrastructure was designed and built for that. In your suburban areas, especially as you move out into some of the more rural fringes, the high voltage side was never really designed for that. So it may need to be strengthened, especially if you're going to put in a large fast charger at the end of the route where the bus turns around. So that may be cost effective, and we have found some routes that are cost effective, but it does depend on your local lines company, your local funding model, and how engaged your particular government is with decarbonisation and what they're anticipating to happen.
Thank you. Next question is, how have the rostering and scheduling tools been adapted to cater for e-bus requirements, for example, refueling and charging?
Yeah, that is actually quite an interesting question. And sometimes these are the sort of things that come up against the culture of an organization. Most routes and scheduling have grown organically, and things have been added on because a new route was won under tender, so it's tacked onto the bus that was available. So sometimes when the transition to electrification is undertaken, it's a good time to look at that and say, can we do this better? So yes, the schedules, the routes often need to be re-looked at, reorganized, and the focus needs to be around the energy consumption. Because it doesn't matter whether you're running diesel or electric, if the bus is doing large unpaid routes to go from the end of one scheduled route to the start of the next route, it's inefficient. It doesn't matter whether you're consuming diesel or the state of charge in your battery. So when we put these blocks together, Bolt will often highlight the fact that this route is very inefficient. And we have had some quite interesting discussions as to why things were scheduled like that. And sometimes the depot scheduler will say, well, it was like that when I came here. I assumed that was right, so I carried on with it. So yeah, good question. So what you're seeing now is that the scheduling tools schedule on energy efficiency as opposed to driver. Historically, it used to be based on the driver, his breaks, his lunchtime, his convenience. Now, it's not to say that the electric bus is inconvenient, but it's to say that the scheduling can be done more efficiently, and maybe the turnaround point for those buses at a different point. So yeah, good question. There are commercially available tools. So Bolt, when we do an analysis, will show scheduling. And a number of the fleet owners that we operate have recently had upgrades from their supplier, which include scheduling for electric buses.
Thank you. I will take the last question. How do funding and procurement models vary across countries?
Yeah, now this we've seen substantial difference, and the procurement especially is something you have to consider carefully. If individual fleet owners are looking to purchase vehicles, they have a certain amount of leverage, and it depends whether you're left-hand drive or right-hand drive. Because if you're going to be ordering buses out, for instance, out of China, and they drive on one side of the road and you drive on the other side of the road, you might find that your procurement process becomes a bit more difficult, as does factory acceptance testing, and you might find some unusual aspects where, for instance, bar graphs run the opposite way to what you used to. So that whole logistics and procurement becomes quite important. Some countries that we've worked with have a centralized procurement where the government transit authority purchases all of the buses and then gives a lease out to the fleet owners where the capital cost of the bus is reduced, but that is offset against a contractual agreement where the fleet owner agrees to run that schedule of routes with those key performance indicators for X number of years. If they pull out of that, well, then the full capital cost of the bus then becomes payable. So that gives you a feel for the different range. Here in New Zealand, we have a slightly different model where we have typically a central transport organization that schedules out and tenders all of the routes, and individual fleets tender for those routes. So that makes it a lot more competitive, and we're a small country, so that might work quite well. If you're a large country with a large population, with a very heavy density, with a need for standardization where multiple fleets, for instance, could be using an opportunity charger, then central procurement makes a lot of sense. But again, don't underestimate the lead times, and sometimes the bureaucracy gets in the way. So I hope that gives people a bit of a range of how things may work.
Thank you. So we're at the end of our webinar session. Additional questions will be answered directly via email. So please feel free to follow up directly with Kristian via the contact details shown on the screen. And I would like to thank all attendees for joining today. Thank you for your time, and thank you, Kristian, for the early morning presentation.
Well, yeah, great. And I'm sure there are a few people who ended up getting up earlier than I did. So I hope people found that useful.
Thank you so much.